प्यारे बच्चों, today we will start another type of oscillator. It is called Wien Bridge Oscillator using operational amplifier. And first of all, we will draw a circuit for Wien Bridge Oscillator using operational amplifier. So, circuit of this oscillator is like this. This is the feedback network, which is a combination of, here we are using series combination of R and C, and another network is parallel combination of RS. This is the output, and at inverting mode terminal we have two resistances. One is feedback resistance. Suppose this is the R1, and suppose these are 4 points A, B, C, which is grounded, and here is a point D. So this structure is like a Wien bridge. Wien bridge is like this. Here we have two resistances. This is RF R1, and here we have parallel combination of RC. Here we have series combination. And these are points A, B, C, and D. So this operational amplifier is connected between B and D. So we can assume that, so here at these two terminals we have operational amplifier plus minus, and this is grounded, C is grounded. So what is the basic concept of this? In RC phase shift oscillator, we cannot vary frequency. So this is, in Wien bridge oscillator, we can vary frequency from 20 Hz to megahertz. So megahertz. So we can achieve variable frequency. This is audio oscillator. So for basic amplifier, here input is at inverting terminal, non-inverting terminal. So we are using both type of feedback. Here from output we have connected input at the positive terminal and also at the negative terminal. So both type of feedbacks are utilized, positive and negative. Negative feedback is utilized to stabilize the gain. Negative feedback to stabilize gain. Okay, and positive feedback means no phase shift. Output and input are at the same place. So total phase shift provided by this feedback network must be 0, and at balance condition, phase shift provided by this balance bridge is 0. So that's why we are using a bridge here to provide 0 phase shift. Now we can find out frequency of oscillation for this feedback network. Derivation of frequency of oscillation. What is frequency of oscillation for this network? Suppose this is the Z1, series combination is Z1 and parallel combination is Z2. Then we can use here series and parallel combination. So this is the series combination and here we have a parallel combination. And this is Z2 and this is Z1. Output here is V0. This is the V0, and at this is the feedback. So what is feedback factor for this? Feedback factor for this is output fed back to the input. What is the feedback signal? So feedback is connected at this positive. So this voltage at this terminal is VF with respect to ground. Then we can write this is feedback signal upon output. This is the feedback factor. Now what is Z1 and what is Z2? Z1 is the series, that is we can write R minus JXC. You can also write R minus J upon omega C. And what is Z2? Z2 is the parallel combination of these two, that is RL in parallel with minus JXC. These are two impedances. So you can write what is this voltage ratio of these two. This is the feedback. You can use potential divider here. Total drop from A to ground is drop across this plus drop across this. And this is the drop only across this. So you can write here, this is the Z2 upon Z1 plus Z2 by using potential divider. So this is the voltage drop across Z2, means parallel combination of this, and V0 is the total drop. So you can replace these values. Z1 is this, Z2 is this. So Z2 is the parallel combination, and what is parallel combination for this is, you can write R into minus JXC divided by R minus JXC. So you can write here Z2 is the parallel combination of this. This is you can write this is R into minus JXC upon R minus JX. This is the Z2 and Z1 is this. This is R minus JXC plus Z2 means plus this R minus JXC divided by R minus JXC. So you have to simply place these three values Z2, Z1, Z2. Z2 is the parallel combination of these two and Z1 is series combination of these two. So you have to put all these values and after solving you will get beta equals, this is minus J R X C. This is cancelled out, LCM is same, and you will get R minus JXC whole square minus JRX, or you can write beta equals minus JRX divided by, this is R square plus this square, that is minus XC square minus 2AB, that is minus 2JRXC minus JRXC, or beta equals minus JRXC R square minus XC square minus 3JRXC. We find out frequency of oscillation. Simply divide by, suppose divide by minus JRXC. Then you will divide this, beta equals 1 upon R square upon minus JRXC minus XC square upon minus JRXC, and this is, that is plus 3. Again you can write, you can say beta equals 1 upon you can use separate two parts, real part is 3, and for this when you will multiply by J, you will get here, that is plus JR square divided by RXC, and when you will multiply by J, you will get minus XC square upon RXC, or beta equals, so this is also J here, Again you can write 1 upon 3. Here 1 R is cancelled out, 1 XC is cancelled out. You can write plus 3. You can take J common. This is R upon XC. This is minus XC upon R. So again, what is value of this? See, this is the 1 upon omega C. This is for capacitance. So you can write here. After replacing the value of XC, you can get this beta. This is the feedback factor, 1 upon 3 plus J R omega C minus 1 upon R omega C. And what is about this A beta? A beta is 1 plus RF upon R upon 3 plus this. Why? Because gain of amplifier is this 1 plus RF upon R, because we are using non-inverting part. So what is the condition? Total phase shift provided by feedback network must be 0. Therefore, imaginary part, this is 0. That is, this part is 0. And from here, you can obtain frequency of oscillation. So this implies this is equal to 1 upon R omega C, or you can say omega square equals 1 upon R square C square. Omega equals 1 upon RC, or 2 pi equals 1 upon RC. Therefore, this is given by 2 pi RC. So this is the frequency of oscillation. So you can obtain this frequency of oscillation from here. You will put imaginary part. This is the imaginary part. Increase this imaginary part equal to 0. When you will put this imaginary part equal to 0, you can derive frequency of oscillation. So this is the frequency of oscillation. You can also calculate condition on gain. What is the condition? Condition can be obtained. This is the frequency of oscillation. You can get also condition. Condition on gain. So at oscillation, imaginary part equals 0. Therefore, A beta This is 1 plus Rf upon R divided by 3. And according to Barkhausen criteria, this magnitude of this must be greater than or equal to 1. Therefore, 1 plus Rf upon R upon 3, this must be greater than 1. Or from here, you can get Rf upon R, this must be greater than or equal to 2. And this is the condition. So this is the condition. This is the condition for oscillation. So this is all about our Wien Bridge Oscillator using operational amplifier. So what is the basic concept for this? In Wien Bridge Oscillator, we have a variable frequency of it. So we can generate a variable frequency oscillation because we have adjustable values of capacitances and resistances in this Wien Bridge Oscillator. Whereas in RC phase shift oscillator, we have fixed values of RC. That's why we can generate variable frequency by using Wien Bridge oscillator. And at balance condition, phase shift provided by this is 0. So since we are using operational amplifier and phase shift provided by operational amplifier is 0 because we are using non-inverting mode. So total phase shift provided by operational amplifier is 0. So feedback network must be such that phase shift provided by feedback network must be 0. So we can use this criteria by using Wien Bridge oscillator. First calculate feedback factor. So feedback factor is simply this voltage Ef upon V naught, and from here we can calculate feedback factor, and from that we can achieve frequency of oscillation for Wien Bridge oscillator. So that is all for today.